In the previous video, we saw that different filter implementations can have different sensitivity to coefficient quantization. So in this video, we'll take a deeper look at how different implementations can be analyzed in terms of their sensitivity to changes in the coefficient. And we'll do this by taking one of the coefficients in a circuit and changing it by a small amount and studying the effect that has on the overall circuit implementation. So there are two quantities that we can consider in this case. So one would be the effect on the transfer function itself, so h of z. And a typical way of doing this would be to look at the derivative of the transfer function with respect to the parameter of interest. So mk here is an arbitrary multiplication in our circuit and can in the ARMA model be either bk or ak. Or we could instead look at the zero and pole placements by looking at how the zeros are affected by changes in the parameters b in the feed-forward part of the ARMA model, and how the poles are affected by the coefficients ak, so the feedback parameters in the AR part of a general ARMA circuit. In order to address the first question, how would the transfer function change if we were to change an arbitrary multiplication in the circuit, let's consider a generic example where we have an input x of n, we have an output y of n, and then somewhere within the circuit we have a multiplication mk. And what we want to study is what happens when you take this multiplication and you change it from mk to delta mk, mk plus delta mk. And that will lead to a change in the output, and we're interested in the magnitude of this change related to the magnitude of the change in the actual multiplication. Now, if you have an input here to this particular multiplication, and that gets multiplied by mk plus delta mk to the output, that's equivalent to taking the input and separately multiplying them with both of the two parts of this component and then adding them up back together again. And viewing it in this way allows us to sort out what happens for the signal from xn up to this point and for the signal from this point to the output, and separate that out from the change in this particular multiplication. So to that end, let's define two signals, so u of n and v of n. U of n is the signal before the multiplication takes place, and v of n is the perturbation signal, which is inserted after the multiplication takes place. So connecting these two branches through a multiplication of delta mk leads to the system that we just saw. And now we can define transfer functions from x of n to u of n, and from v of n to y of n. So the transfer function fk of z tells us what happens to the signal as it passes from x of n to u of n, and the transfer function g of k tells us what happens to the signal when it enters at v of n and passes to y of n, the output of the entire system. And now, if we connect these two branches through the multiplication delta mk, leading to this change in the output signal, it stands to reason that the change in the output signal should be the signal path from x of n to u of n times this change in the multiplication times the transfer function from this point to the output, since transfer functions multiply if we have a concatenated system. Now there is one problem with this argument, and that is that if we were in fact to connect u of n and v of n, we may actually alter the transfer function from this point to that point and from this point to that point. And the reason for that is that typically these multiplications don't exist in isolation. So typically the circuit itself will have some feedback from the output to the input. So connecting these two, because of this feedback, may actually alter the transfer function from x of n to u of n, and equivalently from v of n to y of n. However, one could argue that these effects are small, so if we just look at small-scale perturbations in this effect, then the added effect of the change in the transfer function will be negligible compared to the effect that this connecting them in the beginning will have. And this can be made rigorous by noting that the output before the multiplication is simply the input to the circuit times the effective transfer function from that input to the output, and that is given as the nominal transfer function plus the change we have due to the inclusion of this delta mk. But one can show that the change in the nominal transfer function is only of the first order in this coefficient delta mk. So the change in the transfer function from the input to the point before the multiplication will be the original one times a first order component in delta mk. And the same argument can be made from the output signal as well, or the transfer function from the point after the multiplication to the output. So the difference or the change of the perturbation in the output is given by the transfer function subject to the change in caused by delta mk plus the input after the multiplication. And one can show that this change as well is also on the first order. And then we have that the perturbation input after the multiplication is simply the size of the perturbation times the input before that. And what this implies is that if we consider the change in the overall transfer function defined as the change in the output divided by the change in the input, similar to an ordinary transfer function, we see that this can be worked out to be the product of the transfer function from the input to the point before the multiplication and the transfer function after the multiplication to the output times the size of the multiplication plus second order effect. And this follows from the combination of these three formulas here. So in particular, if we're interested in the derivative of the transfer function subject to one of these multiplication factors, we can obtain that from this expression by simply dividing each side with delta mk and then letting delta mk go to 0. So this is from the definition of the derivative. And doing that in this case, we'll see that this order term will vanish, and what we're left with is the product of these two transfer functions. So to summarize this, the derivative of the transfer function with respect to multiplication can be worked out as the transfer function from the input to the point before the multiplication times the transfer function from after the multiplication to the output of the circuit. So having figured out those two transfer functions, we get the derivative by simply multiplying them together. We can verify this result through a simple example. So here we have a circuit with an input x of n, an output y of n, and one single multiplication c of n. Deriving the transfer function for this whole system yields that it's 1 plus c z to the minus 1 divided by 1 minus c z to the minus 1. This minus c is that we haven't included the minus in the feedback here, and the plus is the general formula for the feed forward of an ARMA system. But here we're using the multiplication both for the feedback and the feed forward, which makes it slightly different than a general ARMA system. So in this case, it's straightforward to take the derivative of this system with respect to this coefficient c. And if we do that, we simply see that it's given by this expression. So 2c to the minus 1 divided by 1 minus c z to the power of minus 1, and all of that squared. But we can also use the result we just derived in order to figure out this result. So in order to do that, we need to figure out what is the transfer function to a point before the multiplication, and what is the transfer function from a signal inserted after the multiplication to the output. So doing that gives us two systems. So one which is the transfer function from the input to the point before the multiplication, and we can remove this part which is not interesting or relevant for that part of the study. And then we can look at the transfer function from a point after the multiplication to the output, and then we disregard the input in that particular consideration. So first deriving or obtaining the transfer function f of z, so the transfer function from the input to the point before the multiplication. That is given by c to the minus 1 divided by 1 c z to the minus 1. And in the other case, for a signal inserted after the multiplication, we have two branches here leading to the same place, giving us this 2, and then we have the feedback part here, which gives us the 1 minus c to the z minus 1. And taking these two expressions and multiplying them together again yields the same result that we got from the direct differentiation of h of z, which it should. Now, let's consider a question on this, trying to figure out these relevant transfer functions. So in a pure AR model like this, what would be the transfer function from the input of the circuit to a point before the multiplication? And in this case, the multiplication of a minus a1 in this case. So what is the transfer function from x of n to u of n? That is f of z given by u of z divided by x of z. Is it the following, 1 over 1 plus a1 z to the minus 1? Or is it 1 over the second order polynomial given both the coefficients? Would it be z to the minus 1 divided by this first order polynomial? Or would it be z to the minus 1 divided by the second order polynomial? Or should we have the coefficient a1 in the expression as well? So should it be a1 times z to the minus 1 divided by the second order polynomial? Well, the correct answer is option number 4. It should be this expression. And one way to see that is to note that without the z to the minus 1, we have the transfer function from the input to the output as a general transfer function of an ARMA model. And the only difference in u of n from y of n is that it's delayed by one time step, which introduces this z to the minus 1. So that gives us option number 4. Now, let's consider the second part of the question. So what is the transfer function from a point after the multiplication to the output? That is, what is the transfer function g of z given by y of z divided by v of z, where v of z is the signal inserted after the multiplication. And you have the same options as in the previous case. So 1 over first order polynomial, 1 over the second order polynomial, c to the min over the first order polynomial, c to the minus 1 over the second order polynomial, or the same final option. The correct answer is option number 2 in this case. And one way to see that is that if we look at the circuit from this point, it's the same as the circuit from this point. So it doesn't matter if we add the signal here or if we add it to this addition. The point here will still be the same, so its effect on the output signal will be the same. So that means that the transfer function from v of n to y of n will be the same as the transfer function from x of n to y of n, and that is the transfer function of this general AR system, which is given by option number 2. So given the answer to the 2 previous questions, we could also figure out how sensitive is this circuit to a perturbation in the coefficient a1. And all we have to do is to multiply together these 2 transfer functions from x of n to this point and from this point to y of n. And if we do that, we get that derivative of the overall transfer function of this system, h of z, with respect to a1 is given by this expression. And that could of course be verified also by directly taking the derivative of the transfer function from here to here once we have that expression. So one of the things that we can note with this expression is that the sensitivity of the circuit or the transfer function will be larger if we have a z which is close to one of the poles, simply because we will then be dividing by a smaller number here, leading to an increase in the magnitude of this quantity. And this will be true even if we look at the relative sensitivity. So even if we look at the magnitude of this quantity divided by the original transfer function, which would be 1 over this polynomial. Since we have the square here, we would even see an increase in the relative sensitivity if we are closer to the poles. So in the next analysis that we'll look at the sensitivity in particular of the poles with respect to these coefficients, and we'll see similar results there. In order to study the sensitivity of the zero and poles with respect to the coefficients of our circuit, we return to the rational transfer function that we have for the ARMA model. And we have the 2 polynomials b of z and a of z, where b of z defines the zeros and where a of z defines the poles. And we could write it either as a polynomial in the coefficient or as a product of terms involving the zeros in case of b and the poles in case of a of z. So in order to study the sensitivity of a pole, for instance, with respect to a coefficient ak, what we need to do is we need to differentiate p of k with respect to a of k. And that can be obtained from this expression by taking partial derivatives of both expressions and equating them. In other words, if we start with this polynomial a of z written in these 2 ways, if we take the derivative of a of z and consider the first term here, it's simply the derivative of a polynomial, which is easy to take, and we can then evaluate that at a particular pole of the system. So if we evaluate it at pole pi, what we will get for this derivative is simply pi to the minus k, and that's easily proven by simply taking derivative of this with respect to ak, which only leaves z to the minus k, and then we insert the value of the pole to get the final derivative. But we could also take the derivative of the second term, and the way to do that, since we're taking derivatives with respect to ak, we can use the chain rule. So we can first take the derivative with respect to z of k, or the pole position, and then take the derivative of the pole with respect to a using the chain rule. So taking the derivative of the second part using the chain rule gives us the derivative of this expression with respect to z evaluated at pi times the derivative of the pole divided by ak. So this is slightly more complicated than the previous case, but it can be straightforwardly worked out and shown to be equal to 1 over pi to the power of m times a product which involves the distance between any other pole and the pole of interest. And then we get the multiplication with pi divided by ak, which is the sought quantity. So to get the derivative of the pole with respect to the coefficients of the circuit, we simply need to take this expression and equate it to that, and then divide by this expression here in order to isolate p of k, or the derivative of p of I with respect to the coefficients a of k. So doing that yields the following expression. So if we have the polynomial that we started with, a of z, and p of I is one of the poles, namely one of the roots of this polynomial, then we see that the derivative of the pole with respect to the coefficient is simply given by p of I to the power of m minus k divided by this product of differences of the pole positions, and here the difference with respect to any other pole except the one under consideration, pi, which is given by this product. So we see two things in this formula. So one is that if you have a pole which is closer to the unit circle, generally this term will be bigger. We'll also see a second effect in that if you have another pole, p of L, which is close to the pole of interest, then the derivative with respect to a coefficient will generally be higher, because this distance will be lower, and since we divide of that, that will increase the magnitude of this. And what this tells us is that if we have many closely packed poles in a system, it will also be very sensitive to perturbations, simply because we'll have many of these small terms that appears in the denominator of this expression that captures the derivative of the pole position with respect to the coefficient. This tells us something important about how to implement systems. So if we're in the need of implementing the following fourth order AR model, as we see here, we know that even if all of these coefficients are real valued, we could choose to split the polynomial defined by these coefficients into a product of two second order polynomials with real coefficients, which means that we could take this system, we could implement it as a cascade of two second order systems as follows. However, if we look at the sensitivity of these systems to change in one of their parameters, we'll see that this system is less sensitive than this system. And the reason for that is that since we saw that the sensitivity is determined by the distance to the other poles of the system, if we were to perturb a single component in this one, it would be affected by the distance. So the position of a particular pole would be affected by the distance to all three other poles, and they could be close. While in this case, if we are to perturb either A11 and A12, that will only affect the poles that are associated with this part of the system here. And there will be only one additional pole to the pole under consideration. So the distance to that will be at least as large as the distance to the closest pole here, or larger, meaning that this system will be less sensitive by the previous expression. And we could do the same argument for the second branch. So generally separating the poles into two different branches by splitting the fourth order system into a cascade of second order system will improve the sensitivity performance of the implementation. So generally it's advisable to implement it in this form rather than in this form. And this is also similar to the result that we saw in the previous video when we had a more heads-on approach to study the sensitivity. So let's consider the expression that we were working with, namely the derivative of the pole position with respect to the coefficient, given by this ratio of two quantities, p of I to the power of m minus k, divided by this product of terms involving the difference or the distance between the two poles in the complex plane. So if for some L not equal to the I that we are considering, you have a pole which is in the same place, you would clearly get a division by zero in this formula. But what does that mean in practice? Does that mean that the corresponding term pi minus pa would simply be removed from the expression? Does it mean that if you look at the pole pi as a function of the coefficient ak, that function would not be differentiable at the particular value ak? Or is the question simply misguided, since any rational transfer function cannot have multiple poles in the same location? Correct answer to the question is option number 2. So the division by zero here would indicate that the derivative becomes infinite, meaning that it's not differentiable at this particular point. And we could always solve this by taking those multiple poles at the same place and moving them into two separate second-order branches, and thereby making the system more robust. Otherwise, we would see that we would have a very large sensitivity of the particular pole placement to small perturbations in AK. And it's good to note here that the derivative is only talking about what happens in the first order effects. So obviously you would not have an infinite displacement of the particular pole if you were to perturb AK. We can apply more or less the same analysis also to look at the sensitivity of the zeros of the transfer function with respect to the coefficients bk, where the zeros are simply the roots of the nominator polynomial b of z. And also in this case we can relate the polynomial to a product of these terms involving the zeros explicitly. The only difference in this case is that we have the constant gain factor b0, which cannot be included here. So doing the same analysis, we see that the derivative of the zero position with respect to a given coefficient is given by the same example where we now included this b0. So at least for all zeros from 1 to m, their derivative with respect to the bk, where k goes from 1 to m as well, where m is the model order, is given by a very similar expression, only differing in the inclusion of this b0 and the fact that we're looking at zeros and not poles anymore. But the argument becomes the same, that if we have a lot of closely packed zeros in our transfer function, that also increased the sensitivity to perturbations of the overall system. And the argument in this case is exactly the same as we had for the poles. So what this means overall is that if you can implement your system as a cascade of second-order system, this will always increase or decrease the sensitivity to perturbations in the system components or in the multiplications involved, both in terms of the feedback part, which we saw previously, and also in the feed-forward parts given by these b coefficients. So if you can implement a system like this, then you should ideally, instead of trying to implement a fourth-order system in direct form by simply stacking the component on top of each other and building a large fourth-order system in this case. So to summarize, we've seen that the sensitivity of a particular filter implementation can be studied both in terms of the effect it has on the transfer function and the effect it has on the zeros on the poles. In both cases, we get the result that higher order systems generally have higher sensitivity to quantization of the particular coefficients within the circuit implementation. So a way to combat this higher sensitivity of higher order systems is to break them into a cascade form and implement them as a series of lower order systems, where each such lower order systems have lower sensitivity to the quantization effect on the coefficients that are involved within that particular subsystem.